Hi, this is Tarik Rashid, Advanced Artificial Intelligence class. The subject is Simulated Annealing, second part. The first part, we explained it in the earlier class, and the second part is a practical class. So Simulated Annealing is a probabilistic optimization algorithm, which is inspired by the annealing process in metallurgy, where material is heated and then slowly cooled down to reduce the defects and reach a stable crystalline structure. Now, who invented simulated annealing? Well, first time in 1983, it was the algorithm published in a paper, famous paper, titled Optimization by Simulated Annealing. It was in the Journal of Science, and there were three authors, Scott Kirkpatrick and C. Daniel and Mario P. Vesey. So, relation to Metropolis algorithm, simulated annealing based on earlier Metropolis algorithm, which was coined in 1953 by Nicholas Metropolis and his colleagues. And they introduced this algorithm. Now, it is a metaheuristic optimization technique used to find best solution, best approximate solution, and using the fitness function or a function. Now, it does this by occasionally allowing worse solutions in the early stages of the search to escape local minima. That's a common issue or common problem in optimization algorithms, and gradually becoming more selective as the temperature parameter decreases. Now, this is the flowchart. Start initializing the temperature and initializing the solutions, and then generate new solutions, and then take the delta energy, which is the current solution minus the previous solution. And if the delta E less than 0, then accept it, accept that solution, come to here. If no, then you go to Metropolis condition, which is probability equals exponential minus delta E over T, and there will be a random number in between 0 and 1. And if P, this value, greater than R, the random value that we coined a value, we toss a coin, and if that tossing coin is R, if P is greater than R, then go to here, get the accept the solution. If not, then go to temperature and decrease it. And here, if the temperature minimum greater than T, go to get the solution. If not, then go back to regenerate. And another way also to explain this algorithm, initial point, we initialize it, and then we get the neighbors of this point using Gaussian distribution, and then we determine the fitness function of that solution and get delta E. If delta E less than 0, accept it. If delta E less than 0, accept it. If delta E greater than 0, go to get a random value, toss a coin, and then if random value less than the Metropolis condition, then accept solution, otherwise go back to here. So that was the algorithm. And here we have starting point, and that's descendant of the direction. This local minima, there could be local minimum more, and that's the global minimum that we have. Now, here the initialization, we have X old and X new, and here the steps of the algorithm, which that's the Metropolitan, and here decreasing the temperature by cooling factor. Alpha is cooling factor. It has to be greater than 0, less than 1. And here the cooling factor, we have it. And that is the Gaussian distribution, how we find a new value, new solution. New solution equals old plus the Gaussian, which is that standard deviation max minus min over 6, because if we have uh, level of confidence 3, 3 multiplied by 2, that will be 6. That's the 6 come from there, the level of confidence of probability. And n is the number of random samples that we throw over 2. Now, that's delta E equals new fitness minus all fitness. And that's the condition that we explained. So if delta E less than 0, accept it. If not, then we go to Metropolis. That's Metropolis. R should be in between 0 and 1. Okay. And that will work with it. So here, practical example, that's the fitness function z 2x1 plus x2 square. And imagine that we have x greater and equal 0 and less than equal 9. That's the condition. So that's our fitness function. We work on it. So initially, we try to get initial temperature and initial solutions. We have these solutions because we have x1 and x2. First solution is 4 by 6. Second solution is 6 by 4. Third solution is 4 by 8, and so on and so forth. So now we have random values of x's, 5 solutions, and these are we plug them into this fitness function, 2x1 plus x2, and we will get these values. Z1 is 44, Z2 is 28, and then the average is 47.9. Now, the temperature we start with kind of 500. Okay, so we start with 500. That's the because then we will have this average. The average value is multiplied by suitable number. Therefore, maximum temperature is initial temperature. So here we're trying to find the initial temperature. Initial temperature, it's 500, but then it's roughly 500 because we have the average here, and we multiply it by 10, like choosing temperature. So it will be, initially we start with 500. So then we cool the material from 500. So the step 2 final temperature is 10. We stop at 10, and then step 3 is temperature factor we say temperature factor, cooling factor, 0 to 1, in between 0 to 1. So we select 0.5. Now, here we select one of the solutions, which is 5 by 7. We had 5 by 7, this one, we take that solution, and we plug it into our fitness function or objective function. We have 2 multiplied by 5 and 7 squared. So we will have 49, and 49 for the 7, and 2 multiplied by 5. That's 10. 10 multiplied by 10 plus 49, it's 59. So that's the first fitness we have, objective function, and in the initial temperature was 500. Now, second iteration, what we do, we multiply temperature by the cooling factor, which is 500 multiplied by 0.5, 250. So the temperature is cooled down, and then we will try to find next point. Well, next point depends on the old point plus the Gaussian. We throw some R's, random values, each time for each component of the solution. This solution has 2 components. We all, in this example, because our objective has 2 dimension, x1 and x2. So here we plugged in the values. Max is 9 because our dimension x greater equals 0 and less equal 9. So 9 minus 0. I mean, this, if you go back to old, so that's what we said it. That is if that's from the very beginning, that's x1 and x2. So the max 9, and 0 is the min, over 6 the level of the confidence, 3 sigma, so that will be 6. 1.5, we'll find the sigma 1.5. Now generate random number here. This R, we select 4 R's, 0.72, 0.72, 0.15, 0.32, and we sum them up and minus how many R's we took. 4 numbers, 1, 2, 3, 4 over 2, so it will be 1.97. So because we had sample n is 4. Now, likewise, we will do with x21. X21 is found. And we will do with x22. X21, the first x was found. And same thing we will do with x22. Again, for every x, we select new R values. And we have old value is 5, and for x2, while for x1 was for x2 is 7, and for x1 was 5, as you can see in the example. So 7 multiply, and then here is basic multiplication and summation. So x22 is 7.3, and x21 is 4.9. That's new. These are new values for x1 and x2, and we try to plug them into the objective function, and we will get 59.32. The previous objective function was 59 only. If you go back to previous objective function, was 59. Z1 was 59. Now, current objective value is 59. Now we subtract this one from the old one. Subtract Z2 minus Z1, that's delta E, the delta energy. So 0.32. Compare 0.32. 0 greater than 0.32? No. So this solution will be rejected. This solution will be rejected, or apply Metropolis, because 0 is not greater than this one. If it was 0 greater than this one, it means your data energy smaller than 0, it will be accepted. But because 0 greater than delta E, it cannot be accepted. So we go to Metropolis condition. Metropolis condition, we toss a coin between 0 and 1, we'll get value 4.92. And then R should be less than equal this value, which is delta E over T to the power exponential. So here is we have the value, the temperature 250, the delta E minus 32, which there's a sign here, and we found 0.99. 0.99 greater than this 0.495, which was the R when we toss a coin. So we will accept the solution, because according to Metropolis, this solution is accepted. Otherwise, we ignore this point. So now we go to iteration 3. Likewise, we accepted this point, the previous point, x21. We plug it into this one. We will have sigma in that way. We'll find it. And then we throw some R's, 4 R's, and then number of R's over 2. That's how we find. So x31, this iteration, 4.44. Likewise, we will do for x32. X32 equals to old one, which is 703, plus the information that we have. And here is the result of x32. Now, answer, we can find that x 4.4 and 5.3, we plug them into objective function, and we will find 39.42. So it means by decreasing the temperature, the solution gets better. As we say, when you lower the temperature, the metal will get better shape, and it gives you better shape or optimum shape. So that is the idea of this algorithm, and we can see that delta E is now less than 0. Again, this will be accepted. This solution will be accepted. And then when we go to iteration 4, the solution will be accepted. So these values will be accepted. These values will be accepted. 4.4 and 5.53 will be accepted for the next solution. And this is the summation of the all iteration on the results. Thank you very much for your interest in this algorithm. So stay tuned and thank you. If you have any problem, that's my email, and you can send me an email if there's any problem.